All right, so we're going to go over number 8 since that was the highest chosen preference, or someone just felt like writing a bunch of 8s. And it's this, guys, remember, if you're working on a different problem, that's fine. Groups in the back. But you need to keep it down low enough that I can actually hear myself. Appreciate it. All right, so you get this car going over the bump. Oh, this is kind of like opposite of the problem that we did for the when we did example problems. This time it's going over the. So this is one that, because it's talking about forces, in this case, of the rest of the forces that are out by the road on the car at its highest point. Because it's talking about forces, you need a force diagram. All right, in your Y. So, what I would suggest, let's see, what we're going to put in our Y. Is the car in circular motion? Yes. At this middle point, it is. So this is, let's see, this is number 8. Right. So, the car is moving in a circle. Not for long, but just for a little bit. So must accelerate towards the center. Of the circle. And then I think that's probably good for that part. And then you can come down here and say, okay, well, what force is going to be downwards? Gravity. So the weight of the car is going to be grabbed down. I'm predicting there's going to be some type of normal force up on the car. And then, because it's going around this circle, there must be an acceleration pointing downwards towards the center of the circle, and that would be a centripetal acceleration because it's pointing towards the center of the circle. Remember, centripetal only indicates the direction of it, that it's towards the center. So that would be a Y for this. You've gotten into understanding that it is in circular motion, so you know the direction of the acceleration. And I think that would be all you would need really for the force diagram, is showing those. So we can jump right over here and do Newton's second law. Which way, just for the mathematics, which way do you guys want to call positive? Up? Okay. So some of my forces, I would have the positive normal force minus the weight. That's going to equal the inertia and a negative acceleration that points towards the center of the circle. So negative a sub c. And I want to know the normal force. So normal force equals F sub g plus a negative, which is the same as minus, right? So minus m AC. And let's see. Oh, I can substitute in mg minus m. Let's see. What do they tell us about it? They tell us the radius, and they tell us how fast, the speed of it. So, looking at my equation sheet, I'm going to pick to use v squared over r for, substitute that in for my centripetal acceleration. Since they tell me the speed. And now it's plugging in. Let's see. M. What do I got? 1150 for mine. Oh, I'm going to factor my m out, so I only have to put it in once. Less calculator work, right? I can just factor the m out there, a little algebra. So, 1,150 kilograms. G, I remember off the top of my head, 9.80 newtons per kilogram. Minus V, the speed of my car is 6.75 meters per second. So, 6.75 meters per second, that quantity squared, over my radius, which is 20 meters. And I can solve for my normal force. Let's see, where the I got for mine 8,650 newtons. Seems right. And then, of course, the directionality of that would be downwards. Then we have part B. If the speed at the highest point is above a certain maximum value, the car will lose contact with the road. Calculate this maximum speed. So if the speed is at the highest point, if it's going to lose contact, that means is it still going to be going in a circle if it loses contact with the road? No. So what's happening here is, remember, we have to have that acceleration to go in the circle. And the force that's providing that acceleration is actually the weight. And so if we're moving so fast that the weight can't provide enough force to accelerate us towards the center, then we stop going in the circle. Okay? No, it's just like trying to run around a corner or something, and you can't make it because you're going too fast. The friction on your feet can't provide enough force to do it. So, at the point where this happens, is we're still, just before it, we're still going to be accelerating downwards, and we'll have that force of gravity down, but we won't have any more normal force, because all of the gravitational force will be needed to keep the car in this circle. So we'll jump into some of the forces. Equals MA. This is part B, by the way. And you'll have F sub G as your only force. I'm going to take down as positive because I don't feel like writing a bunch of negative signs. And MAC. Do the same substitution I did this time. M B squared over R. And also substitute in there for F sub G. So it's mg equals m b squared over r. Ooh, anything cancel out? The m. That's nice. And I know my g is going to be 9.80 meters per second squared. My v is what I'm looking for. My radius is still going to be that 20 meters. Solve for v. Most common first time mistake through this will be forgetting that v is squared in the step above, and people will solve for v squared and forget to square root their answer to get v. So be careful of that. All right, we're going to do number 2. The ball in the string revolved in a vertical circle of this. They showed this. Its speed is this. And its mass is this. Calculate the tension of the string. Oh, nice. They already did like the force diagrams for you, except they left off one part. So we'll have to clean up the one thing that they forgot to put in there. Yeah. So, writing textual-wise in this, why I would have like ball in circle. So, accelerate towards middle. Fire, good. You know, those type of things. But definitely some indication that you understand that the acceleration of the ball is going to be towards the center of the circle, since it is in circular motion. They've already put in our two forces here that are acting on the ball at these 2 points: the tensional force and the weight in both cases. Notice that the weight stays constant, right, downwards towards the center of the earth, but the tension keeps changing its direction, so that it, from an outside frame of reference, so that it stays perpendicular to the velocity. But what did they forget in this force diagram? Not the strength, because remember in the diagram what's important is to have the forces and the acceleration. They forgot the acceleration. Alright, so to get complete credit on this, you would need to indicate that the acceleration is these directions. The top is pointing towards the center, and the bottom is pointing towards the center. Alright, so, and that's why we can label it centripetal, because it is always pointing towards the center there. So, let's do part A. Let's see, which one do they ask? Which is which? For A, the tension string when it's at the top, and B is when it's at the bottom. Okay, so A at the top. Back to our old standby, Newton's second law. So our forces at the top would be, which way do you guys want to call positive for this top situation? Up or down? I'm going to call it down. I like down because then I have everything in that diagram is positive. So I'm going to have FT1 using their notation just to make it clearer, plus mg equals the inertia times the acceleration, which is a sub c. And they want to know, let's see, what do they want to know? The tension, they want FT1 and FT2. And I know the speed is 410 and the mass is 0.3. So 410 and 0.3. Yeah. So I'm looking for FT1, so good idea mathematically to get it by itself. I'm going to have MAC minus MG. Yes, good, math-wise. Okay, so FT1 equals M. I know the velocity, I know the radius, so I'm going to use V squared over R for my equation sheet. Might not be a bad idea to write up here A sub C equals V squared over R in the equations, minus M times G. I know M, 0.3 kilograms, right? I know V, 4.1. What's yours? Oh, you're not on this problem. 4 something. Okay, so yeah. And then R, I think they give it to us as 70 centimeters. Should I use it as centimeters? No, what should I make it into? Meters. So 0.7 meters. And so I would substitute all that in. Right? FT1 equals 0.3 kilograms. Watch me run out of room. 4.10 meters per second. Square that over 0.70 meters. That's at 70 centimeters in meters, minus 0.3 kilograms times 9.8, running out of room, newtons per kilogram. And I can solve for FT1. And then I look and say, okay, I'm ready to do the second part. The second part is at the bottom. And my weight has stayed in the same direction towards the center of the Earth. But now my tension is pointing away from the Earth because it's still towards the center. And my acceleration is now pointing away from the Earth towards the center. So really it's a very similar setup here. I'll just do it down here. So I start with Newton's second law again. In the forces I have, which, you guys want to call up positive? Is that okay for the bottom? Okay. I have FT2 minus mg equals m times acceleration centripetal. Again, FT2. But if you notice this time, they end up adding together rather than subtracting like last time because of the change in direction of the tension and the change in direction of the acceleration. And then it's very similar substitution to what you did before. I have no... V squared, you mean? Is the speed squared. Yeah. Alrighty. Let me know if you need help solving the math on that one. Alright. We're doing number 4. We got a car going around a turn at this radius on a flat road. Oh, this is just like that video we saw on the first day talking about circular motion, right, London? Yes. So what force was pointing towards the center of the circle when that car was going around the flat corner? Friction. Friction was. So friction is the only force that could be pointing towards the center. And they're wanting to know what's the maximum speed. So we do need a force diagram on this, but I would start with, car in circle. So accelerate towards center. Friction. Points towards the center. And causes acceleration. So it's that friction that's pointing towards the center, causing the car or allowing the car to turn the corner. So my force diagram that I need for this is going to draw a nice flat road. I'm going to draw the car as if it was coming right at me. In my limited drawing ability. Nicole, don't make fun of my drawing. See, look at that. I already knew she was going to make fun of me.
Oh, okay.
The car is coming at you. If the car's coming at you, the wheels look square.
Okay, yeah.
Don't stand in front of a car unless it's not moving. But look, sometimes you'll see they look like squares.
No, I do it. No, it's not an issue.
So the car is coming at us, so we'll indicate that with a little arrow coming at us. Remember, that's how, call that V. That's how you indicate an arrow coming out of the board. So we'd have the weight down, we'd have the normal force up, and we would actually have, now, remember, friction always opposes motion or possible motion. So if the car is coming at us, and we'll say the center of our circle is over here, way to the left, if there was not friction, which way would the car want to move? If there was not friction, which way would the car want to move? You'd want to actually move out to the right, you know. But because there is friction, it's able to go around the circle and thus able to accelerate in that direction. So that would be the expected force diagram. The V is showing you that the car is coming at you. The V stands for velocity or speed, and that is an arrow coming at you. Remember, you've got an arrow at you and an arrow away from you. So an arrow that's coming at you looks like that. An arrow going away from you looks like that. That was a long time ago when we talked about, oh, it's like an arrow that has feathers and an arrowhead coming towards you or away from you. Thank you. I practiced. Nicole still laughs at me.
I appreciate it.
All right. Start with Newton's second law. Oh, sum of the forces in the x equals m/a(x). Oh, all that stuff again. Old piece of cake. Which way do you want to call x and y? You want to call up and down y?
Yeah.
And side to side x? Okay. So in the y, we've got force normal minus f sub g. How much acceleration in the y direction? None, right. So force normal equals the weight. Right? London, you getting this one? Sure? Alrighty, good. And then in the x direction, no, we only have one force in the x direction. Frictional force. And that's going to equal the inertia and the acceleration in that direction, a sub c. Oh, I remember from my equation sheet, frictional force is mu force normal. Oh, force normal is the weight, right? Right? Oh, mu mg equals mac. You cross out the m. So what's the correct answer to that second part then? Is the result independent of the mass of the car?
Yes.
Yes, because you crossed out the m's. True. Good. And then that's what it means to be independent, right? You don't have to consider the m's in your calculation. So does it matter if it's my big truck or, you know, a little smart car going around this corner? Not at all. Not at all. Let's see what I know. Oh, mu g equals v squared, the speed squared over the radius then. And what do they want to know? I've lost track of that. The fastest you can go, right?
Yeah.
And I don't care about that 1180. The 65 I care about, and the coefficient, which is 0.80. So I want to get v by itself. So mu g r equals v squared. I know mu, that's my 0.8. I know g, 9.8 newtons per kilogram. And I know r for me was 65. Time to plug and use that calculator. What will be the most common mistake Not square rooting your answer. That mu stands for the coefficient of friction. It does. Yes. So we're going to look at number 6 now. 6 is one of the 2 on this assignment that I didn't need a force diagram for, 5 being the other one. Because there's no forces mentioned in here. Could I still do one? Sure. But I wouldn't be graded on whether or not I had one. So you've got, that's actually one of my son's favorite rides when we go to the Townsfield Fair. About 30 years old too, the ride. It's kind of scary, but. So you have, the riders are moving around in a circle in this radius. How many revolutions per minute will the riders be subjected to when acceleration is that? So, let's see, what number is this? 6? 6. So, rider moves in a circle, so must accelerate towards the center. Might even put the faster they move, the more acceleration. I think that kind of brings it also back to this problem a little bit. So let's look at what they want us to look at. They want us to end up telling them how many revolutions per minute. So that's that rotational speed, like the one we did in the example problems. So we could find the linear speed and then convert that to rotational speed, or we could say, well, I know that I could figure it out by knowing some other facts. Let's do it by figuring out the linear speed. So I'm going to use my good old friend A sub c is the linear speed v over r. And in here, for my A sub c, they tell me it's 1.9 times gravity. So 1.90, and then gravity, which is 9.80 meters per second squared, equals v squared over my radius, which is 9 meters. And I do a little math, and I get that v equals some number. Because they told me that the acceleration, sorry, I'll flip back here. My acceleration, centrifugal acceleration, 1.9 times that of gravity. So what they're trying to do is make the acceleration make more sense to you. No, I'm just getting started. And so I got a V of 12.94526.941 meters per second. Hopefully you got something close to that, yes? Most common mistake will be to forget the square root, yeah. All right, so now that's my linear speed. That's how fast I'm going in meters per second around the circle. I want to change that linear speed. I want to change meters per second, meters over seconds. I want to multiply that by the number 1 twice and end up with revolutions per second, per minute, right? So I need to change the meters to revolutions. So I'm going to put meters on the bottom and revolutions on the top. Anyone remember what's the relationship between a revolution around a circle and the linear distance around a circle? Right. In one revolution, you go 2 pi r, the circumference. To go around a circle once, the length is 2 pi r. It is, depending upon the radius of your circle. Right? Now, so good, I got revolutions. Now I need minutes. Seconds up top, minutes on the bottom. What's the relationship between minutes and seconds? 60 seconds in 1 minute. So I'm going to end up with, let's see. My meters per second starting is 12.9. Let's rewrite it. I've got 12.945 meters per second multiplied by 1 revolution over 2 pi. I forget what my radius here was. 9 meters? 2 pi times 9.0 meters. I'll finish this recording and post it. Times 60 seconds over 1 minute. And once I do all of that, so times 60 divided by 2 pi, 2 pi times 9, I get 13.7 revolutions per minute. And I'm hoping that's right. I'll check it. Hold on one